Good morning, afternoon, Math 2 crew. We're now going to talk about completing the square. Our essential question is, how can you solve quadratic equations without factoring? Well, we did in the previous lesson, we used square roots. We didn't have to factor anything, we used square roots. But there's another technique called completing the square. And before we discuss completing the square, I want to talk about what a quadratic looks like in terms of an area model. So I will now discuss area models and quadratic equations or quadratic expressions. So let's take a good look at this area model. Some of you have seen this before, some of you have never seen this before, so it might be new, so bear with me. So what I want to do is I want to represent x squared as an area. And the way I do that is I take this tile, it's called an algebra tile, and you'll see that there's x squared written in the center of it. And what that represents is the area of that square, x squared. What that implies is that the area of, let's go back there. Oops, wrong button there. Let's click on it again. What that implies is that the length and width of this shape is x and x. Okay? The area would be x times x, or x squared. And so I have a quadratic. It's a simple one with just x squared written. Okay? It's my quadratic. And that's the area model of that quadratic. Let's make it a little more complicated. Let's add some x terms. And so I'm going to take this shape. Now I'm going to take an x term, place it there. And so I have two of these x's. And so what this would represent, again, is something a little different. The shape is x and x, which gives us x squared. And the length and width of this rectangle here, right here, is slightly different. Since we know this distance from here to here is x, and this lines up nicely, then we know this rectangle has the same length of x, but the width is 1. Okay? And so this rectangle has a length and width of x and 1. All right? So you see how that works? So let's show that one more time separately, though. So I'm going to move this over. So this shape has a width or length of 1. The distance from here to here is x. And so when you multiply x times 1, you get an area of 1, or x. Okay, so this x is the area of this rectangle. All right, good. So let's erase that. Let's move it on over. And so to represent this as a quadratic, we have x squared plus we have two x's, x and x. So the area of that shape is a quadratic called x squared plus 2x. Understand? Yeah. Now, let's go one step further. Since I know that the shape has an area of x squared plus 2x, I wonder if I can fill in this small little piece here to kind of complete it so that it's just one square. I wonder if that's possible. Well, let's see and find out. Okay, let's see what I can do here. Okay, so I think I found this piece here, and it looks like it might fit there. And if I place this piece above here, it looks like it's the same width as the x tile, and so we know that width here was 1, so I'm assuming now that this tile here is a 1 by 1, and it's faint, but I do see a number 1 here. Let's use a different color. I do see a number 1 here. And so what that means is that the area of that square piece is 1. Okay, so let's place that there. And there we go. So that has an area of 1. And so this area model represents this quadratic. We've got x squared, right, for our larger square. The rectangles here, there's 2 of them, it's 2x. And then the single piece here in the corner, if we add that up, that's 1. And so this is the area of this perfect square. And now it's a square. Before it wasn't. When I added that one tile here with area 1, it became a perfect square. And so let's talk about the length and the width of this perfect square. We had said that this was a square, and so we said this was x and x. We talked about this rectangle here having a length and width of 1, right? We also said this piece here had a length of 1. Okay? And so I just found the length and width of this perfect square. It's x plus 1 and x plus 1. And so what I want to show you is that the area model would be, the area of it would be found by taking length times width. And so the area is equal to x plus 1 times x plus 1. Right? And if you were to FOIL that, it would equal x squared plus 2x plus 1. And looking at this here, it would be x plus 1 squared. Okay? Now, again, I just made a comment. I said that x plus 1 squared is equal to x squared plus 2x plus 1. And if you FOIL, you will see that. Got your outer, inner, first, outer, inner, last. So check that out. That would be the answer. Now, so our area model represents several things here. It shows us the length and width of this perfect square. And when you know the length and width of a perfect square, you are in fact factoring the quadratic that represents the area of this square. So what I've just shown now is that x squared plus 2x plus 1 is going to equal the length and width of that perfect square. Okay. And so the idea here is that if you have a perfect square, then you can factor it using the length and width of that perfect square. And that's an important feature. So this would not be possible if this square was not perfect in terms of its length and width. If it didn't have the same length and width, it wouldn't be a square, it would be some other object. And so the goal now is to figure this technique out and use it repeatedly when we're factoring quadratics or when we're trying to change the quadratic to make it factorable, and hence computing the square. So let's try a couple of more examples here. Let's talk more showy. So let's take this shape. Remember, that was missing. So what I noticed, let's just talk about what I noticed. X squared, I've got 2 x's. I've got this piece called 1. Good. It's a perfect square. If I were to add another segment here, that would not be a perfect square. It looks more like a rectangle, right? So how would I make this a perfect square? Well, let's remove these pieces first, and let's see. I've got 2x, and I've got an x here, so I think I need to add another x. So now looking good. Now my length and width are identical, but I'm missing some tiles here. This piece has to be complete. And so take these one by ones. 1, 2, 3, 4, right? And so the 4 pieces there make this shape into a perfect square. And so if I were to think about it and look at the total area, the area would be 1x squared. How many x tiles? 1, 2, 3, 4, 4x. And I also have 4 1 by 1. And so that would be a perfect square, quadratic. And again, if you look at this, this would be x plus 2, x plus 2. And if you multiply x plus 2 times x plus 2, you get the area, x squared plus 4x. And so the factored form of this quadratic is x plus 2 and times x plus 2, which is x plus 2 squared. That's why it's called a perfect square. Okay? Now let's try one more example using this model. Let's grab a couple more of these. So again, that's not a square. Now we're missing pieces. Also, this segment here, this side is longer than this side. So let's add another tile here. Okay, so that looks correct. Got to add a couple more of these guys. Wow. Okay, so let's write down what we have here. This is now a perfect square again. Nice square shape. Again, this would be, let's count out the area. So I've got x squared. But now I have 3 x's and 3 x's, so double that. 3 on one side, double it, you get 6x. And then if you get 3 here and 3 times itself, 3 times 3 gives you 9. Okay, I think I'm starting to see a little pattern here, where if you look at the side length, if you get the x, and you got the 3 x's, if you double that, you get the 6x, and then half of that 6x is 3x again, and 3 times 3 is 9, so I'm starting to see a pattern here. Now, the factored form of that perfect square, x plus 3 squared. So, there's something going on between, I think, between this number, the middle term, 6. Taking half of it gives us 3. But taking 3 and squaring it gives us 9. Something's going on here with these shapes, the factored form, the perfect square. I think I know what's going on. So, with that said, what we're going to do now is we're going to try to create perfect squares by adding information to them. So we're going to move on to the lesson. I hope the aerial model, if you've seen it before, maybe some of this came back to memory and it's understandable. But if you haven't, we'll do more of this and it may make more sense in just a bit. Okay? So sit tight. I'm going to change my slides over, and I'll be right back. Okay, so let's get our books out. We're going to be on page 459, section 8.8. So we're on page 459, section 8.8. And our goal is to solve quadratic equations without factoring. And we're going to do this by what we call completing the square. So first things first, we're going to explore completing the square. Now, I'm going to read. Please follow along in your book. If you haven't got that out yet, get it out now. We're on page 459. It says the diagram below represents the expression x squared plus 6x plus c with the constant term missing. So in other words, we don't know what the number is for c. A, complete the diagram by filling in the bottom right corner with 1 tiles to form a square. Those are the 1 by 1 tiles. So this is not a square. It is like an L shape of some sort, or a right turn. It's not a square yet. We're missing objects here. And so what we learned was that we can add these tiles to the shape to make it a square. And I'm going to cheat here. I'm just going to use my drawing tool. I'm going to draw these out. So I can see that if I just do this, out there. Let's move it. That's close enough for me. So they almost look like perfect squares. A little off, but that's okay. So those are my other squares that we're missing, the 1 by 1 tiles. Okay? So we've just finished section A. Complete the diagram by filling in the bottom right corner, and we did it. Okay? So now that I have that, the shape itself is a complete square. Okay? Now let's go to the next section and see what the next step is. So now we're looking at the next couple of segments or sections in this exploration. So now I'm looking at part B. Part A was to draw the shape. We did. We filled in the number of 1 by 1s to make this a complete square. And then it asked, part B, how many tiles did you add to the expression? Well, if you count them out, there's 1. These are all 1 by 1s. And so it looks like there's going to be a total of 9. So there are 9 1 by 1 tiles. So I'm going to say 9. It says write the trinomial represented by the algebra tiles for the complete square. And so x squared, there's 1. How many x's are there? There's 3 and 3. There's a total of 6. And how many 1 by 1 tiles? There's a total of 9. And so this is the trinomial. It's 1x squared plus 6x plus 9. Now, to part B. It says you should recognize this trinomial as an example of the special case a plus b squared equals a squared plus 2ab plus b squared. Recall that trinomials of this form are called perfect square trinomials. Since the trinomial is a perfect square, you can factor it into 2 binomials that are the same. And so what is being said here is that if you know the length and the width, you'll see that they're identical. They are the same. That's what it says here. That right here, it says that they're perfect squares, right? And if I'm not mistaken, does it say that factored into 2 binomials that are the same, saying that the length and width are the same of this square, and it must be because it's a square. So this would be x plus 3. We'll repeat that. It's 1x plus 3. The x is already written. And that is the factored form of this quadratic. Another way of looking at that would be, since sometimes these boxes and the color change doesn't seem too clear, but what they're saying is that the x squared plus 6x plus 9, if you were to factor it, it equals x plus 3 squared. And again, if you use your diamond and check that out, you would get that answer, okay? It's a perfect square. Now, I'm going to keep moving forward. Focus, concentrate, and think about what we're doing. So now we're going to reflect. And I'd like you to spend some time reflecting before I start reflecting. So take a look at this reflection at the bottom of the page, part 1A and part 1B. The video is going to be silent now. It'll play, but it'll be silent for approximately 3 minutes. Okay? So 3 whole minutes, we're just going to let you think about 1A and 1B and attempt to answer it before I answer it, okay? So starting now, you may begin. So that's about 3 minutes, so I will begin. 1A. Look at the algebra tiles above. The x tiles are divided equally, with 3 tiles on the right and bottom side of the x squared tile. How does the number 3 relate to the total number of tiles? How does the number 3 relate to the total number of 1 by 1 tiles you added? Okay, so how does the number 3 relate to the total number of tiles? Well, the total number of tiles is 6, right? And so how does 3 relate to it? Well, let's think about it. 3 is half the amount of the total number of tiles. So think about it. You have 3 here, right? 3 on the left side, right? And you also have 3 here. You look here, you have 3 here. And so the total number of tiles is 6x. And so you can think of it this way. How does the number 3 relate to the total number? Well, if you double 3, you get 6x. Or you can say that the number 3 is half of the total number. So I'm going to say the number 3 is half the total number of tiles. So okay? How does the number 3 relate to the number of 1 tiles you added? Well, it looks like 3 appears to be, well, the total number of 1 tiles, first of all, is 9, right? Total of 9 of them. And 3 appears to be related in a way so that if you square it, you get the total number. So how does the number 3 relate to the number of 1 tiles I added? I'm just going to write the number 3 is number 3 when squared is the number of 1 tiles added. All right. Now let's read 1b. How would algebra tiles be arranged to form a perfect square trinomial x squared plus 4x plus c? How many 1 tiles must be added? How is this number related to the number of x tiles? All right, so how would they be arranged? Well, first of all, it looks like that based on our previous example, if you have 6x tiles, then you have to have the same amount on either side. So you'd have to divide 6 by 2, right, to get 3 x's on either side. So if there's 8 x's here, if you divide that by 2, you're going to put 4 x's on one side of the x squared, and on the other side you put the other 4. And then how many tiles would be added? Well, in the middle, lower, not the middle, but the lower right-hand corner, you'd have 4x by 4x, which gives you 4 by 4, which is 16 tiles. So how would the tiles be arranged? You'd have to place half of 8x is on the right, and bottom side of the x squared tile. Okay? Now half of 8x is on the right and bottom side of the x squared tile. I get that. So half of 8 would be 4x. Okay? And doing that, how many 1 by 1 tiles? Okay? Well, I'm going to draw a little picture. So we have not pretty. Okay. So there's 4 x's, right, and 4 x's there. Right? Right. If you want me to put them little x's, I can. Now, so how many 1 tiles must be added? Well, we said there's 4 here across the top, 4 here across the lower left-hand corner. And so you can see that there's going to be a total of 16. So I'll extend this out. Again, it's not pretty. They're supposed to be perfect squares, and mine aren't. Oof. Oh, that's awful. Fix that. I don't think it's fixable, but we'll try. Not bad. Not great either. So yeah, this would be the, there we go. So there's 16. So let's write that. Sixteen 1 tiles must be added. And how is 16 related to the number of x tiles? Well, let's think about it. There are 8 x tiles, right? There are 8 x tiles now. Now, I want you to be careful about how I do this. This is going to be a subtle trick. But it looks like, remember, that I took the 8x, right, and I divided it by 2 because I had to put 4 of these x's here, right, on the right-hand side of x squared and on the bottom side of x squared. So I had to divide 8x by 2. I know that. So if I take 8 and divide it by 2, that gives me 4. Okay, now I'm still thinking about how the number of x tiles is related to this number called 16. Now, look at 16 and 4. If you square 4, like I did here, 4 and 4, 4 times 4, it gave me 16. So now if you square 4, right, so now if you take 4 and square it, you end up with 16. And so that's how it's related. How is the number of tiles, x tiles, related to the number of 1 tiles added? It's this. I'll use a different color. The number, and instead of spelling, I'm just going to use a symbol, the number of 1 tiles is found by taking half the number of x tiles and squaring forgot the ing, and squaring that amount. Okay? Wow, that was quite a reflection. So let's see if we can use this technique to complete the square of an expression and see how that's going to help us solve a quadratic. Now, just to make this full circle here, this original quadratic here, we now found that as a completed square, it's x squared plus 18, or 8x plus 16. And that is a complete perfect square quadratic. And that was the idea, to find c, and we did. Okay, I'm going to keep moving on. Maybe another 5-6 minutes, we'll see. So we're looking at page 460, example 2, completing the square. And let's see if we can add the information to make sense of this example. Okay. It says complete the square to form a perfect square trinomial, then factor the trinomial. So here's my incomplete trinomial. Now remember, this would normally be written this way. And they would say complete the square. They wouldn't put the c there. But since it's an example, they're attempting to explain that, hey, we're missing a constant here. Something's missing. Let's place the right number there so that we can factor this quadratic, make it a perfect square. So how do I find that missing number? Well, they call it c. Now, since it's a quadratic, the middle coefficient is always called b. And so to complete the square, you take the middle coefficient, 12. And to complete the square, you take 12 and divide it by 2. And that's what's going on here. This is the part of the page 460 that I wanted you to read. And what you do is to find c, which is the number here that's missing, right? To find c, you take b and divide it by 2, and then take that answer and square it. And so what's b again? It's 12. Divide 12 by 2, and you get 6. And 6 squared is 36. So I'll show the step. 12 divided by 2 is 6. Square it, and you end up at 36. And so the value of c is 36. Okay? So that's what's going to go in this box. So when you write the trinomial, it's x squared plus 12x plus 36. Now, this can be factored into a perfect square trinomial. And so we'll bring this down. And the factored form is x plus 6 squared. Now you might not see how that's factored. So if you don't see it, then use your diamond or your bow tie. Set up your diamond. This is 36. Right? And this is 12. And you can see that 6 times 6 is 36. And they're both positive. Because when you add 6 plus 6, you get 12. And so the factored form here, if I was to work this out, it would be x plus 6 times x plus 6. And again, the way you write that as a power is x plus 6 squared. So I hope that helped, this little diamond here that gives you some organization to find the factored form as two binomials. Okay, so how did we create this perfect square trinomial? We had to complete this square by taking half the middle term and squaring it. You're going to notice, too, that half the middle term, 6, right? Half of 12 is 6. It's also found in the x plus 6, here, 6, in the perfect square factored form. So that's important. Okay. Here's another example. So identify b, negative 26. Find the value of c, okay? We take b, take half of that. Half of 26 is 13. It's negative 13. This becomes negative 13 squared. And negative 13 squared is 169. And that's positive. So the value of c is 169. So when we rewrite the trinomial, it's z squared minus 26z, or plus negative 26z, plus 169. Now, if you were to factor this the old-fashioned way, I'll do that once I use my technique here. You'll see how this works. Okay, here this becomes z minus 13 squared. And again, the minus 13 came from half the middle term. See that negative 13 squared? I want to show you the factored form. So let's set up my diamond and change my font color. So we have 169, negative 26, and you'll see that negative 13 and negative 13, the sum of that is negative 26, but when you multiply you get positive 169. And so that would be z minus 13 times the quantity z minus 13. And writing that as an exponent, that would be the solution. Hopefully it starts making some sense. Now let's use this technique of computing the square to solve an equation. Okay, so we're going to solve this quadratic. We're not going to factor the quadratic, and it's factorable. But we're going to set this up by using the technique called completing the square. And so the first step, and I did skip a page, example 3, and so my apologies, but the first step when completing the square is to always isolate the first two terms of your quadratic. And so if there's a constant there, you want to move that over to the other side, okay? And you do that by adding or subtracting the value of the term, its opposite. So if it's minus 1, then you do the opposite, you add 1. So I'm going to do that. So I'm going to take this, and I'm going to add 1 to either side. So this becomes not 0 anymore, it equals 1. And so see this blank term here, something that's missing? Something's missing here now? That's what we're going to do to complete the square. Okay, so that's the strategy, is to create a completing the square situation by looking at the first two terms in a standard form quadratic, and then finding that third term by completing the square. So that third term, negative 1, was moved over, so I can have a blank third term to do this. So add b plus, or b over 2 squared to both sides of the equation. So let's find that amount. What is this amount? So let's take this. Let's take half of 2. So I'm going to work this out up here. So I'm going to take negative 2, take half of it, and that gives me negative 1. A very important number here. But then I take that number, and according to the directions here, I square it. So now I take 1, square it, and that becomes positive 1. That positive 1 is what I add. So now let's do that. Plus 1. Now remember, if it's an equation, then you add a number to the left side. You must add that number also to the right side. So I already have a 1 here. See it? The purple one is still there. So I'll just bring that down. So I just added 1 to the 1 that's already there. It comes from this situation. Okay. Now it says factor the perfect square trinomial. So on the left side here, we can factor that. So that becomes, now remember, this half of the middle term, that minus 1, that becomes the factored form. And it's going to equal, what's 1 plus 1? 2. It says apply the definition of square roots. So let's take the square root. And so we're going to take take the square root of each side. You take the square root, remember you have two answers, plus or minus 2. And so we get a nice reduction here. And we end up with x minus 1 equals plus or minus the square root of 2. So we have two solutions here. We have a negative solution and a positive solution. So by adding, here's the difference here. You're going to add 1 to either side. And you end up with, now this plus 1 here, adding 1, what I like doing is like taking that value and just placing it right here. So my solution is going to be x equals 1 plus square root of 2, or it's going to equal, excuse me, 1 minus the square root of 2. And so, why do we complete the square? Here's why we complete the square. We complete the square to end up with the situation so that we can take the square root and solve it. So when you have a quantity x minus 1 squared, taking the square root of that allows you to solve for x. And that's the whole reason why we complete the square, so we can take the square root and solve. Okay? Now, we'll keep going here. Let's look at another question. So your assignment, before I forget, is complete all the notes on section 8.8. So your assignment is to complete all the notes on 8.8. On Wednesday, we'll work on some of the practice questions. So tonight, all the notes. Got it? Good. Now, B. Let's write the equation in this form. So again, we look at the first two terms of the standard form quadratic. We want to remove the constant, place it on the right side. So it's plus 16, so subtract 16, and we end up with and why do we do that again? Because we want to create a situation where we don't have a constant term, and we can find the constant term by completing the square, which makes this a perfect square quadratic. So we can take the square root. So let's find this value by using this technique. Okay. So what is b squared, or b over 2 squared? Well, that's going to be half of negative 8. So half of negative 8 is 4. And 4 squared, oh, negative 4, forgot that. And negative 4 squared is 16. And so we add 16. Okay, so I'll write this out. So you end up with x squared minus 8x plus 16, that's what we just found there, positive 16, equals negative 16 plus 16. See that? So factor the perfect square trinomial, so we factor this here, and that's going to be x. Okay, now the half of the middle term is negative 4, so it's x minus 4 squared. Again, if you don't see that, use the diamond and you'll see that it's x minus 4 squared. And that's going to equal 0. Ooh, very nice. And so, apply the definition of the square root. Okay. You're going to end up with x minus 4 equals plus or minus the square root of 0. Now, there is no such thing as a positive or negative 0. 0 is 0. It's neutral. Neither positive nor negative. Right? 0. And so, when you apply the definition of the square root, there's only one solution here. It's 0. So, I'm going to clean this up. It's x minus 4 equals 0. And then solving this by adding 4, you get x equals 4. So there are no two equations to write. Hate to disappoint you, but that's the case. Okay, with that said, there are more examples that you need to work out. There's a very important section, I believe it's examples 5 and 6. I will talk about those two tomorrow on Wednesday when I see you. Like I always say, please, please, please study hard and learn a lot. And we'll see you soon. Bye-bye.